7.3.2 Hypothesis Tests for a Population Proportion, Lesson 2. Introduction. The hypothesis testing process. In the last lesson, we thought about the main steps involved in a hypothesis test. In this lesson, we consider these 4 steps more closely. Step 1. Determine the hypothesis. A hypothesis is an educated guess that we can support or that can be supported or refuted by data. The hypotheses are based on the research question or the claim we are testing. Step 2. Collect the data. We must make sure that the sample we use is representative of the population. This means we need a sample that is randomly drawn from the population. We use the data from the sample to calculate a statistic, such as a sample proportion or sample mean. The statistic we calculate is an estimate of the parameter. By the way, before I go on, I just want to point out something here. Notice it says sample mean, but we are not doing that yet. That is in a future module. So what we're doing in this module is we're focusing on the sample proportion. We'll get to a sample mean later on, okay? However, what we're talking about here is the hypothesis test process that's going to apply to every hypothesis test that we learn in this class. Okay, step 3, assess the evidence. Look at how strongly the data from the sample supports the claim we are testing. Step 4, state a conclusion. Use the evidence from step 3 to make a conclusion about the claim we are testing. Next steps. Determining the hypothesis. In order to test a claim about population parameters, we create 2 opposing hypotheses. We call these hypotheses the null hypothesis and the alternative hypothesis. Before we go on, you notice that we have introduced new symbols now for these. These are the symbols that we're going to use for the rest of the class. So let me zoom in a little so you can see it. The null hypothesis is always going to be an H with a little 0. H naught is how you say this, or you can call it H sub 0. The alternative hypothesis is an H sub A. So an H with a little a down there. Okay? These hypotheses are statements about the population parameter we are examining. In all hypothesis tests, we assume that the null hypothesis is true. This allows us to make computations and construct a sampling distribution to help us make a decision. The null hypothesis states that the population parameter is equal to a specific value. We use this to create a sampling distribution that helps us assess the evidence from the sample data. We often think of the null hypothesis as an assumption of no change, no difference, or no effect. Okay? We're going to do a lot of practice in this section about how to construct null hypothesis versus alternative hypothesis. But the idea is that the null hypothesis is always assuming that things are normal, that nothing has happened or changed. In this module, the parameter is the population proportion P. So every problem that you do in this section is going to have a P involved. The null hypothesis states that the population proportion is equal to a particular value. So notice here that H naught, remember this is the null hypothesis, says P equals a value. This is always going to be the null hypothesis, that P equals something. Now, what about the alternative hypothesis? The alternative hypothesis is a claim implied by the research question and is an inequality. Remember, an inequality means that it's not an equal sign. In this module, the alternative hypothesis states that the population proportion is greater than, less than, or not equal to the value assumed in the null hypothesis. The alternative hypothesis is represented symbolically by one of the following. So look, these are the three possibilities for the alternative hypothesis. Either P is less than something. You're going to use that if you think that possibly the proportion has gotten smaller. The alternative hypothesis, so that's if you think the proportion has gotten bigger. Or the third one is if you don't know whether it's bigger or smaller, but you're just going to make a claim that it's different. Okay? Let me write a little bit here. So P is less than a value is going to be for when things are smaller, or you see the word decrease. P is greater is going to be when things are larger or increase. And usually P is not equal to is just if they say something has changed or it's different. So they don't say whether it's bigger or smaller, but they just say, we think maybe it has changed. Okay, so for example, data show that about 60% of students who begin college eventually graduate. A publication of higher education claims that the proportion for STEM is just short for science, technology, engineering, or math. So STEM majors is higher. So again, we know that 60% of students who begin college eventually graduate, but a new publication of higher education claims that for STEM students, that rate is higher. So the null hypothesis then would be P equals 0.60, right? Because we're assuming that the rate for STEM students hasn't changed, right? That's always the null. And then the alternative hypothesis is the statement that you think that it's gotten larger for STEM students, right? So that's what P is greater than 0.60. So that would be an example. The publication claims that the population proportion is greater than 0.60, so this is the claim that researchers want to test. The researchers gather data to see if it supports this claim. So what we're going to do right now is we're going to practice reading a problem and coming up with our own P, and then writing down what the null and alternative hypothesis would be for that problem. Okay, so number one, a population proportion is represented by P. In the following questions, state in words what P represents, then determine the null and alternative hypothesis for each claim below. So let's start with part A. About 57% of registered voters voted in the last presidential election. A student claims that less than 57% at our college plan to vote in the next presidential election. What does P represent? So let's read this one more time. So about 57% of registered voters voted in the last presidential election. So what is the student claiming then? A student is claiming that less than 57% of students at our college plan to vote in the next presidential election. So the claim has to do with the percentage of students at the college, not total registered voters, right? So P is going to represent the proportion of students at our college that plan to vote in the next presidential election. Okay, so this is what P represents. And let's go ahead and try to fill out what the alternative hypothesis and the null hypothesis are. So let's start with the null hypothesis. So the null hypothesis, remember, that is saying that what happened before is still the same. So the null hypothesis here would be to assume that the proportion of students at our college is just equal to 57%, right? Because that's what it used to be. 57% of voters voted in the last election. So P is going to equal 0.57. Okay, so that's going to be it for the last election. Okay, so what about the alternative hypothesis? So let's see, does the problem say whether we think that percentage has gotten bigger, gotten smaller, or just different? The key here is this word less than, right? So a student is making a claim that less than 57% of students at our college plan to vote in the next election. So this would be P is less than 0.57. Okay, so that would be the null and alternative hypothesis. Okay, let's try the next example. And I would recommend, you can pause this video and you could try to work it out on your own and then unpause it and see what I did, okay? And then this is a good way to check to make sure that you actually understand this. Okay, but I'm going to go ahead and I'm going to keep going. So let's look at part B. Superstorm Sandy hit the mid-Atlantic region of the U.S. in October 2012. Since natural disasters can bring people together or tear them apart, researchers wondered whether depression rates among Sandy victims changed from the typical rate of 12%. Okay, so what does P represent here? Remember, the researchers are concerned about depression rates among Sandy victims. So let's write this down. P represents the proportion of Sandy victims that were depressed. The proportion of Sandy victims that were depressed, okay? So that's what P is. And so what would the null hypothesis be? Well, they're wondering if it changed from the typical rate of 12%. In other words, 12% is the null hypothesis, right? Because that we're going to assume that it's equal to that it has not changed. So I'm going to write P is equal to 0.12. What about the alternative hypothesis? Well, are the researchers concerned that the depression rates have gotten bigger or smaller or just different? So the key here is this word changed, right? All they're concerned about, or they think that maybe the rate has changed. It's something different, meaning it could be smaller or bigger. So the alternative hypothesis then is going to be not equal to 0.12. Okay, now let's look at part C. After President Obama's second electoral victory, a news organization claimed that a majority, you're going to see this word a lot, so the word majority means more than half, okay? That a majority of adults in the U.S. supported his new gun legislation. So what does P represent? Well, we're talking about the adults in the U.S. that support his new gun legislation. So I'm going to say P represents the proportion of U.S. adults. Sorry about that. That support Obama's new gun legislation. I know this is an outdated problem, right? And we can't, calling it new legislation is weird because Obama's not even president anymore, but we're just going with the terminology of the problem, right? We're sort of putting ourselves back in time here. So let's think about what the null and alternative hypothesis would be. So this is a tricky one because the problem doesn't say any numbers, right? So the key here is this part here where it says more than half, right? Half seems to be the key thing here. So half would be the null hypothesis, but remember, null hypothesis is always that it's equal to that. So the null hypothesis is going to be that p is equal to 0.5. Or you could say 0.50, that's fine too, but we don't need to do that. So that would be the null hypothesis. So what would be the alternative hypothesis? Well, they're concerned that it's more than half. So more than half would be a greater than, wouldn't it? P is greater than 0.5. Okay, so hopefully this makes sense so far, and let's move on to the next steps. So let's practice the hypothesis test process as outlined in the beginning of the lesson. So we're going to do some example problems that use these scenarios we just talked about, okay? So first example, do college students exercise their right to vote? In the 2012 presidential election, about 57% of registered voters actually voted. A student at a local college thinks her fellow students don't really care much about politics. She claims that less than 57% of students at her college plan to vote in the next election. To show this, she randomly samples 100 students at her college and finds that 49 plan to vote in the next election. Let's test her claim at the 5% level of significance. Remember, the level of significance is the rule for how small an event's probability should be in order to be considered statistically significant. So this is going to be a reminder of how to do a hypothesis test from the beginning, and we're going to run through the entire thing. So let's start with step 1, determine the hypothesis. We already did this in an earlier part, right? So we could look up our answer above, or we could just write it down again. Remember, we are assuming that 57% is the same, and then remember, she thinks that less than that are going to vote in her election, or not in her election, but at her school. Less than 57% of students at her school are going to vote in the next election. So this is going to be the null hypothesis and the alternative hypothesis. Okay, step 2, collect the data. If the underlying sampling distribution of sample proportions is approximately normal, we can use a normal probability model to determine if the sample proportion above is statistically significant. Are the criteria for approximate normality satisfied? So whenever the problem asks us that, we need to make sure that 2 things are true. 1, that the expected number of successes and failures are at least 10, and also we need to make sure that it was a random sample. So let's go through these one at a time. So what are the expected number of successes? That's just n times p. And what would n be? Remember, our sample size was 100. So it's going to be 100 times 0.57, which if you use your calculator, you'll see is just 57. Expected number of failures, it would be n times 1 minus p, which is 100 times 1 minus 0.57, which if you work that out is 43. both of those are at least 10. So that means, yes, the criteria is satisfied for normality. Is there evidence that the data were gathered randomly? Well, let's look above at the problem again, make sure that this is true. It says she randomly samples 100 students at her college, right? That was written, we have that written right here, randomly samples, okay? So because of that, I'm going to say yes. The problem states that the sample was random. Part D. We have assumed a value for the population P. Now we need the sample proportion P hat. Remember, P is different than P hat. P we get from the null hypothesis, but P hat is from the sample itself. So let's give the values of the sample size and the sample proportion. So the sample size is 100. The problem says that. So n is 100. What's P hat equal to? Well, let's see. How many people in her sample collected? She said she found 49 people out of 100 that planned to vote, right? So 49 out of 100, which is 0.49 if you use your calculator. So that's P hat. So this is the data that we collected, and now we're ready to move on to step 3, assess the evidence. So in other words, we need to find a p-value and see how unusual is that low voter turnout that she got. Does it prove, or does it reasonably prove, that people at her school vote less, or is it just luck? So let's see. To determine if the sample proportion is statistically significant, we compute its z-score. In order to compute the z-score of the sample proportion, we need the mean and standard error of the underlying sample distribution of sample proportions. Use the population proportion assumed by the null hypothesis to compute these. So what was the null hypothesis? Remember, mu sub p hat would be the mean, and that's just p, and p we get from the null hypothesis, so it's 0.57. Okay, 0.57. What about the next part? We need the standard error, which is sigma sub p hat, and that's going to equal the square root of 0.57 times 1 minus 0.57 divided by 100. So I'm going to put that in my calculator right now, and I'm going to see what I get. 0.57 times 1 minus 0.57. Please do it alongside me in your calculator. Make sure you get the same answer that I do. So I get 0.0495. I know that's a lot of decimal places. I used 4 decimal places, but if you use 3 decimal places, it would be 0.50, right? So you can use either one. It's up to you. Okay, so let's move on to part F. It says draw the sampling distribution with the mean from the null hypothesis on the normal curve below. Show the positions of 1, 2, and 3 standard errors below the mean, and the positions of 1, 2, and 3 standard deviations above the mean. Then identify the position of the observed sample proportion. Okay, so 0.57 goes here, and I'm going to add 0.57 plus 0.0495, I get 0.6195. And if I add 0.0495 again to that, I get 0.669. And if I add 0.0495 a third time, I get 0.7185. Okay, so those are 3 standard errors above the mean, and then I'm going to do below the mean. So if I do 0.57 minus 0.0495, I get 0.5205. And if I subtract 0.0495 again, I get 0.471. And if I subtract 0.0495 again, I get 0.4215. Okay. It also says to identify the position of the observed sample proportion. So what answer did she get when she polled her students? Remember, she got 49%. P-hat was 0.49. So where does 0.49 go on this chart? I'll use red for that. 0.49 is somewhere between 0.471 and 0.52. So maybe it's like right here. This is p-hat, which is 0.49. Off the top of our head, as we're looking at that, does that look like it's super unusual that she got that number? According to this picture, it's not even 2 full standard deviations away, right? It's maybe like 1.5 standard deviations, and that is not that unusual. So I can kind of predict here that her alternative hypothesis is probably not going to be supported by this evidence. Okay, but let's keep going, and we'll see for sure. We're going to find the z-score of the sample proportion. Remember, I just looked at this and said it looks like it's something like 1.5 standard deviations below the mean. So that means that off the top of my head, the z-score is probably going to be between -1 and -2. Maybe -1.5, who knows? We're going to find out right now. So we get 0.49 minus, and remember, P is the value that we assumed from the null hypothesis. So this would be 0.57, and then we have to divide that by our standard error, right? Which, if we go up here, that is 0.0495. 0.0495. So I'm going to go ahead and subtract, or not subtract rather, but figure out what this is in my calculator. So make sure you get the same answer as me in your calculator, and put the top number in parentheses just to be sure. So when I do 0.49 minus 0.57 and then divide it by 0.0495, I end up with, if I round it to 2 decimal places, I get -1.62. Remember I said it would be around -1.5 standard deviations? So this does make sense, right? This agrees with what we were doing before. So let's keep going here. We want to compute the probability that the z-score of this random sample proportion is at least as extreme as the one observed here. What does it mean to be extreme when something is smaller? At least as extreme means that far away or more. Okay? When the alternative hypothesis is P is less than a value, we're conducting what's called a left-tailed test. The p-value is the probability of observing a sample proportion at least as extreme as the one we observed. In this case, at least as extreme means as low or lower. The p-value is the area to the left of the test statistic. So this is a picture of what we are doing here. We now want to find the area to the left of that value. Let's go ahead and write it here. Remember, we had negative 1.62. So it says plot the test statistic on the number line below and shade the appropriate tail that corresponds to the p-value. Well, let me do that in red. So remember, negative 1.62, that's around negative 1.6. So if we were to look here, it would be somewhere around here. Okay, this is what it looks like. We shade to the left there. So we want to find that area. Remember, off the top of our heads, this doesn't look like the p-value is going to be small enough here, right? Because that's a pretty sizable area. So we're going to use technology or tables to find the p-value corresponding to the test statistic computed in question 2G above. And for this, I'm going to switch over to my calculator in a second so you can see how we do this. But remember, when you want to find an area like that, we use what's called normal CDF. So the p-value is equal to normal CDF. And the lower limit is what? Well, we're going to the left forever in that shading, aren't we? So that means that negative infinity is where the graph starts. And then if we go to the right forever, we stop at negative 1.62. Okay, so this is going to be our p-value. And what does this equal? Let's find out. So coming over to our calculator, remember we want to use normal CDF, which is this distribution button. So I'm going to do second DISTR, and I'm going to go down to normal CDF. The lower limit is negative 1 EE99, and the upper limit is negative 1.62. So go down to paste, hit enter, and we get 0.0526. I'm going to round that to 0.053. Okay, so we get 0.053. The p-value is a probability. So what probability does it represent? So this is the probability that the p-value is the probability of observing a sample proportion at least as extreme as observed, assuming the null hypothesis is true. And that's the most important part, right? So again, to remind you of what this means in the big picture, the probability of observing what we did, assuming the null is true, if we get a very low probability, then that means the null hypothesis is probably not true, okay? So let's keep going here. When the p-value is less than the level of significance, it indicates that the sample proportion is unusual and therefore statistically significant. Is the sample proportion for this problem significantly less than the population proportion assumed in the null hypothesis? Okay, well, 0.49, right? Remember, this is what she observed, and it is smaller, isn't it, than 0.57, so is less than 0.57, but possibly not significantly less. So we're going to look at that in a second, okay? So what's the key here? The key is to look at the p-value. The p-value is 0.053. And is that smaller than the level of significance? Well, the level of significance is 5%, which is 0.05. Is this smaller or bigger than 0.05? It is bigger. So it is not significant. So we're going to keep going here, and we're going to talk about this more. So hypothesis tests are all about making decisions. We use the p-value to make a decision about the null hypothesis. So you need to know, here are some extra terminologies that we need. So the level of significance is a rule for how unlikely a significant event should be. This level of significance is symbolized by the Greek letter alpha. So alpha is the significance level. That's all it is. It's a shorthand for the significance level. If the p-value is less than or equal to alpha, the evidence is strong enough to lead us to reject the null hypothesis and support the alternative hypothesis. When the p-value is greater than alpha, the evidence is not strong enough to lead us to reject the null hypothesis. Therefore, we do not accept the alternative hypothesis. Now remember, this does not make the null hypothesis true. We can't prove the null hypothesis because sample data cannot reveal the true value of the population proportion. So let's go ahead and write down what we know. Write the level of significance given above as a percentage in decimal form below. What is our level of significance? Well, the problem said it was a 5% significance, wasn't it? Let's make sure about this. Let's go to the very beginning of the problem to make sure that's what they wanted, okay? Yes. Do we see here it says 5% level of significance? It's usually going to be 5, but sometimes we use a different level here. Okay, so alpha would be 0.05, right? That is how you change 5% into a decimal. So 0.05, remember this is bigger. So let me actually erase that for a second here. 0.05 is bigger than 0.053, right? We wrote that above, but I wanted to write it here as well. So do we reject the null hypothesis or fail to reject it? So again, we need to be less than, something needs to be less or equal to 0.05 in this case in order for us to reject the null hypothesis. So since this is bigger than that, we do not reject the null hypothesis. So we fail to reject the null hypothesis. So do we support the alternative? No, we do not support the alternative hypothesis. Explain what this means in terms of the proportion of students at this college who plan to vote in the next election. Use plain language indicating that this decision was prompted by our data. Remember that failing to reject the null hypothesis does not prove it. Okay, so let's remember what we are doing in this problem, right? Let me go back up to our null and our alternative. So our null hypothesis was that P was 0.57, and our alternative was that less than 0.57, right? However, we're saying that we don't support the less. So we're not going to say that P is equal to 0.57. However, we are going to say that we fail to reject it. Okay? So what does P represent? Remember, she's talking about the percent of students at her college that plan to vote in the next election. So this is how we write the answer in context, okay? At a 5% significance level, we fail to reject. Remember, we're failing to reject the null hypothesis. So we fail to reject that the proportion of students at her college that plan to vote in the next election is 0.57. We fail to reject the null hypothesis. That's what we are saying here. So, in other words, the student's claim the evidence is not strong enough to support her claim that people at her school are less likely to vote in the next election. Okay, the evidence just wasn't strong enough. I should say, though, that it was close, right? I mean, 0.05 is larger than... Sorry, I you know what? I just realized that above I wrote something wrong, so let me fix that here. I said 0.05 was larger than 0.053. So, sorry, I wrote that inequality in the wrong order, so that should have said 0.053 is larger than 0.05, right? That's the thing. In other words, we got that the p-value was bigger than alpha, right? Okay, sorry, I wrote them in the wrong order. Okay, so this is how we write our answer. As explained in the previous problem, the method for computing p-values depends on the type of test, and the type of test depends on the alternative hypothesis. You need to know. So computing p-values. When the alternative hypothesis is p is less than a value, we are conducting a left-tailed test. So this is called a left-tailed test, and the p-value is going to be the area to the left of the test statistic. Okay. When the alternative hypothesis is p is greater than a value, we are conducting a right-tailed test, and the p-value is the area to the right of the test statistic. When the alternative hypothesis is p is not equal to a value, we are conducting a two-tailed test, and the p-value is twice the area of either the tail to the right of the positive or tail to the left of the negative. Okay, so we are going to do some examples of the two-tailed as well, so you guys know how to find that p-value, but really it's going to be just finding one of the tails and then doubling it because the two sides are the same. Something important to note is that when you're doing normal CDF, let me just write something in here. So if you want to find the part that's shaded here, it's going to be normal CDF. And the left is going to be negative 1E99, and the right is going to be the z-score value, right? And if you're doing this guy, then it's going to be normal CDF, and then the left is going to be the z-score value, and the right is going to be 1E99. Right? So this is the difference. When it's left-tailed, you've got to do it that way. And when it's right-tailed, you've got to do it that way. And now, what do you do when it's two-tailed? When it's two-tailed, you're going to do, you can choose either the left or the right. I'm just going to choose the right here. You're going to do just 2 times that. 2 times the normal CDF of the z-score and then 1E99. So all I'm saying is let's just double this guy. Okay? All right. Next steps. In the next problem, most of the computations are done, but we leave the p-value to you. So this one will be a lot quicker, right? So number 3. Before Superstorm Sandy hit the east coast of the United States in 2012, the depression rate among adults was 12%. Knowing that natural disasters can bring people together or tear them apart, researchers wondered whether depression rates among Sandy victims had changed from the prior rate. Let's test this research question at a 2% significance level. From a random sample of 800 residents from the affected areas, 117 were clinically depressed. This was a sample proportion of, and they even do this calculation for us, p hat equals 117 over 800, which is 0.146. Okay, so let's determine the hypothesis. We already actually got these in question 1b. Remember we said that the null hypothesis is that the depression rate is the same, so 0.12. And the alternative hypothesis, remember they were just wondering if it is different now. So we're going to write p is not equal to 0.12. Is this a right-tailed, left-tailed, or two-tailed test? Well, because it's a not equal to, it is two-tailed test. Okay. So we need to check for normality, and they even did that for us. It says to check for approximate normality, we're going to multiply n times p. N is the sample size. It says right there it's 800 people. So 800 times 0.12 is 96. And 800 times 1 minus 0.12 is 704. Are the criteria satisfied? Yes, since both are at least 10. The normality criteria is satisfied. By the way, I'm going to take a brief break here to let you guys know that the code word for this lesson is hurricane. Okay? So that's what you're going to put in the little box, hurricane. Okay, let's move on. We have made an assumption about the population proportion P. We were given the sample proportion, P hat equals 0.146. The sample size is n equals 800. With these, we can move to the next step. By the way, but actually, before I move on to the next step, was this a random sample? They should have asked us to verify that as well. And it says here from a random sample of 800 residents, okay? So let's say that here. Let's say the sample is random and all of the above is true, okay? Or all the below is true. Okay, step 3, assess the evidence. The mean and standard error allow us to compute a z-score, the test statistic. The mean of the underlying sample distribution is mu sub p hat, equals P equals 0.12. And the standard error is, remember, you're always going to get the standard error by using this square root formula. So when you plug in the numbers, remember you're assuming that the P is true from the null hypothesis, you get 0.011. So now we're ready to find the z-score. Remember, the z-score is you take our p hat, which is 0.146, and you subtract the p that we're assuming from the null hypothesis, and then we're dividing that by 800. Oh, no, sorry, not 800. I said that wrong. Sorry, we don't divide that by n. We're dividing that by the standard error, which is 0.011. Okay, so this is what we're going to put in our calculator, and I'm going to round it to 2 decimal places. So we get 0.146 minus 0.112 divided by 0.011. I get 2.36. Make sure you get the same thing in your calculator. So let's move on. This is the first time we have computed a p-value for a two-tailed test. Remember, the p-value is the probability of observing a random statistic that is at least as extreme as the one we have. For a two-tailed test, at least as extreme can happen in either direction. For this reason, we find the area of the tail that lies beyond the test statistic and double it. Plot the test statistic on the number line below and shade the tail that extends beyond it. So what did we get for our z-value? It was 2.36. So that's pretty far, right? That's 2 standard deviations above the mean. So I'm going to go to my red pen here. 2.36 is almost at, is that what it was? Yes, 2.36, okay. So 2.36, it's going to be right before 2.4, so it's this little guy right here. And then also, I'm going to go to the other side. Okay, so what we want is the total of those 2 shaded parts. So I'm going to get the area of the right side and then double it. Note that you can find the area of the left side and then double that one also, because those 2 areas that I shaded are the same. Okay, and again, we need to double it because this is a two-tailed test, and it's really easy to forget to do that, so be careful when you do these problems, all right? So p-value is going to be normal, oops, I forgot to write the 2 times. So 2 times normal CDF of, so I'm doing the right side here, so the shading begins at 2.36, and then the shading ends at 1E99. So let me go ahead and put this in my calculator, and let's see. So we're going to come over to our calculator here. Remember, we want to do 2 times this. So I'm going to go ahead and do that right from the beginning. 2 times, and then I'm going to do the normal CDF. So remember, that's DISTR. So I'm going to do second DISTR. I'm going to go over to normal CDF and hit enter. And then that goes from 2.36 until 1EE99. Go down to paste, and I get 0.018. Now, of course, you could also just do normal CDF and then remember to double it at the end. Just be really careful that you do not forget that, okay? So 0.018 is what I got. So the calculator gave us a p-value of 0.018. So let's go ahead and write that in. Assuming that the null hypothesis is true, what is the probability of observing a sample proportion at least as extreme as the one that we got? It is 0.018, right? That is the p-value. Okay, so what was the significance level? Let's go ahead and look at the problem from the beginning again. In the original problem, it says we want to answer this question with a 2% significance level. Okay, so that is going to be our alpha. So let's come back here. Our alpha is 0.02. Use the p-value to make a decision about the null hypothesis. Do the data support the alternative? Well, we got 0.018, which is smaller than 0.02, right? It's smaller, right? Because 1 is smaller than 2. So what does it mean when we get something smaller? It means that this is statistically significant. In other words, this is what happened was rare enough that we are going to reject the null hypothesis, right? So we reject the null hypothesis and support the alternative hypothesis. Finally, the most important part of this is to write a conclusion that explains the results of this test in plain language. All right, so in the context of the problem. So remember, we're rejecting the null and we're supporting the alternative. So I'm going to talk about the fact that the evidence supports the alternative here. So what was the alternative? Let's recall. The alternative is that P was not 0.12. And remember what P was? It was the depression rate of Hurricane Sandy or Superstorm Sandy, right? Victims. So let's go ahead and write this. At a 2% significance level, let's always write our conclusions starting with the significance level. The evidence supports the claim that the proportion of Superstorm Sandy victims that are depressed is different from 0.12. Okay, so that's, again, this is what the alternative said, isn't it? Because that's what not equal to, right? Remember, they said that they thought that the depression rate had changed. So not equal just means that it's different from. So that's what I wrote. I said, at a 2% significance level, the evidence supports the claim that the proportion of Superstorm Sandy victims that are depressed is different from 0.12. Okay? All I'm saying here is that we support the alternative. The evidence supports the claim that the alternative is true, and I just stated the alternative in plain English. All right, everybody, that's it for this lesson. Thank you very much for watching. I hope the video was helpful.